Adipocytes are often mischaracterized as passive storage units, repositories for excess calories destined to fuel chronic disease. But the reality is far more sophisticated and encouraging. Far from being inert blobs, fat cells are dynamic endocrine regulators. They secrete a diverse array of bioactive peptides known as adipokines, which act as hormones to influence tissues across the entire body. This endocrine role of adipose tissue places it at the center of metabolic coordination, integrating signals from nutrient intake, energy demand, immune status, and hormonal feedback. Rather than harming health, properly functioning adipocytes are essential for maintaining metabolic equilibrium, especially in an energy-rich, dynamic environment. Among the many adipokines secreted by adipocytes, leptin and adiponectin are the most well-studied. Leptin serves as the body's satiety hormone. Produced in proportion to fat mass, leptin informs the hypothalamus about energy sufficiency. When leptin levels are high, the brain reduces appetite and increases energy expenditure. When leptin is low, as during fasting or in undernutrition, hunger rises and metabolic rate drops. This negative feedback loop protects against both starvation and overfeeding. Deficiencies in leptin signaling, such as in rare cases of congenital leptin deficiency or more commonly in leptin resistance seen in obesity, result in uncontrolled appetite and energy imbalance. But this is not a failure of fat cells. In fact, adipocytes in these cases are responding normally. It's the downstream signaling, often impaired by chronic inflammation or excessive nutrient load, that becomes dysfunctional. Adiponectin, on the other hand, is unique in that its levels inversely correlate with fat mass. Higher in lean individuals, adiponectin promotes insulin sensitivity, enhances fatty acid oxidation in muscles, and reduces hepatic glucose production. It also possesses anti-inflammatory properties, dampening the chronic low-grade inflammation associated with metabolic syndrome. Importantly, adiponectin crosses the blood-brain barrier and may have neuroprotective effects as well. Its protective role in cardiovascular health, insulin signaling, and even longevity has been demonstrated in multiple models, suggesting that enhancing adiponectin secretion or action could be a promising therapeutic strategy. Other adipokines such as resistin and FGF21, fibroblast growth factor 21, also contribute to this complex regulatory landscape. Resistin has been implicated in insulin resistance and inflammation, though its role is more prominent in rodents than humans. FGF21, meanwhile, acts as a metabolic thermostat. Though primarily secreted by the liver, adipose tissue is a significant secondary source of FGF21, which enhances glucose uptake, promotes lipid oxidation, and facilitates the browning of white fat into energy-burning beige fat. Interestingly, FGF21 levels rise in response to fasting and ketogenic states, indicating a role in energy adaptation under stress. These hormonal outputs from adipose tissue enable a flexible, system-wide response to changes in nutritional and energetic conditions. The coordination between adipocytes and distant organs is central to systemic homeostasis. In the liver, adipokines influence gluconeogenesis, lipid synthesis, and bile acid metabolism. In skeletal muscle, they modulate glucose uptake and mitochondrial function. In the pancreas, leptin and adiponectin can impact insulin secretion directly, contributing to the fine-tuning of blood glucose control. Even the cardiovascular system and brain are affected. Adipokines regulate vascular tone, inflammation, and neural signaling related to reward and appetite. This distributed influence underscores how vital adipose tissue is, not as a passive depot but as an information processing hub that helps the body respond appropriately to an ever-changing internal and external environment. What's remarkable is how the function of adipose tissue remains responsive to lifestyle and environmental cues. Nutritional composition, physical activity, sleep, circadian rhythms, and exposure to cold or heat all shape adipokine profiles. Exercise, for example, has been shown to increase adiponectin and promote the secretion of beneficial lipid mediators, lipokines, from fat cells. Intermittent fasting and caloric restriction upregulate FGF21 and improve leptin sensitivity. In this sense, adipose tissue acts as an interface between behavior and physiology. It senses environmental inputs and translates them into endocrine signals that reprogram metabolism across the body. Supporting the health of adipocytes by encouraging metabolic flexibility, limiting inflammation, and maintaining proper adipokine signaling, could therefore be a linchpin in strategies to prevent or reverse metabolic disease. In light of these insights, the reputation of fat tissue deserves rehabilitation. Adipocytes are not merely liabilities to be minimized, but sophisticated sentinels of energy and metabolic health. Their endocrine activity shapes how the body uses, stores, and senses nutrients. Through the rhythmic release of adipokines, they coordinate the actions of distant organs, helping ensure that glucose and lipid metabolism remain aligned with the body's needs. The dysfunction seen in obesity and metabolic disease is not intrinsic to fat cells themselves, but often a result of disrupted communication, chronic stress, or inflammation. The therapeutic goal, then, is not the indiscriminate loss of fat, but the restoration of adipose tissue's intelligent endocrine function. By supporting the health and adaptability of adipocytes, we move toward a model of metabolic health that respects the intricate biology of fat and perhaps even uses it to our advantage.